In this video, I will explain the concept of a resultant as it applies to vectors. And specifically, we will take a look at the meaning of this in terms of physical applications using forces. So, imagine we have the following. We begin with some object. Here's an object, a little dot. Okay? And imagine a blue guy comes along. Okay, and he is right there, and now he's going to push up on the dot. So what we do is we draw a little arrow, and the arrow represents the force that the guy exerts on the dot. The length of the arrow represents the magnitude or the size or the strength of the force that this guy is applying to this object here. And imagine further that a little guy, green guy over here, comes, and now he exerts a force on the object so that his arrow looks like, let's say, this. Okay? That is the force that he exerts on the object. Now, it's really important here to understand that no actual arrows exist. These are just mental models that we build. Okay? When you push on something, no arrow appears, correct? So that's just a mental model we build in physics to help us quantify these things. Okay. And now the question is, what is the resultant? Meaning, what is the one force that will move this dot, okay, the way that these two individual forces put together would move it? So the way to do it is as follows. You take, for example, the blue one, and you move it over, right, and you draw a new copy over here. And you draw the new copy right there. And then the resultant is the following. The one I am drawing that is so bright, that is the orange one. There you are. This is the resultant vector. This is the vector that says, instead of having a blue guy and a green guy, although you may have trouble seeing the difference, okay, so the horizontal is the green and the vertical is the blue. The orange is the resultant vector. What this is saying is this. Instead of having two guys, one pushing up, one pushing horizontally, what you can simply do is this. Take your object, get one orange guy, to push along the direction of this arrow. And the result is the same as if the blue guy pushed up and the green guy pushed to the right. So this is what we call the resultant force. Okay? You may want to label this resultant. Okay? This is the same as this one here. In other words, it has the same impact as the green and the blue combined together. This is no different from saying, if you get a bill for $5 and then you get another bill for $5, if you don't want to deal with two $5 bills, you can simply replace them with one $10 bill, right? It's exactly the same concept. You don't want to deal with two forces, so you replace them with one equivalent force that accomplishes the same thing, right? So if you go to a store and you're buying something, $5 once, $5 again, that's the same as just handing $10 over. Same thing applies here. Two forces are replaced with one force. The name of this force is the resultant. Okay? So let's take a look at a more concrete example again. Say you have an object, okay? And one guy, the green guy over here, he'll push on it, and the arrow that represents his force, okay, the vector, looks like this. Another guy comes along, the blue guy, and he pushes this way. So the green one is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 roughly, okay? So the blue guy now is pushing to the left on the object. So you have two forces acting on the object. They're pointing in opposite directions, but the magnitudes are the same. So what this is telling us is the following. Because this is the case, the resultant is nothing. So that means if you are somebody standing here at the object itself, you will not move. Because the forces applied by the blue and green guys simply cancel. They're in opposite directions. So if you're standing on the object and you're the orange guy here, you will not move. So the resultant in this case, we'll call that big R with an arrow to indicate it's a vector. That is 0. Okay, the resultant is 0 in this case. Let's take a look at another example. So these are just conceptual examples, not really mathematically detailed ones. So you have an object over here. And one guy, the blue guy here, he pushes on the object. And here's the arrow that represents his force. So that looks like this. Another guy comes along, the green guy, and he pushes on the same object, and his arrow also looks like this. Okay? So there are two forces acting on the same object, and these forces are in the same direction. So now the question is, what is the resultant? In this case, the resultant is this. You take the green and you add it to the blue. So what results is an arrow that looks like this. Okay? This is the resultant vector. Okay? So what this is saying now is the following. Instead of having a blue guy and a green guy as before, you can simply get one orange guy, right? That is, let's say, twice as strong, and have him apply his force to the object, and the object will experience the same thing as if you had two individual guys pushing on it at the same time. Okay, so this is what we mean by a resultant. So one more time, the resultant is the one vector or force, in this case, you would apply to produce the same impact as several individual vectors or forces. Okay, let's take a look at the case of several individual ones. Okay, so this one will get a little more interesting, but we can do it. There you are. Here's our little dots. Say there's a force acting in this direction. Then there's a force acting in this direction. Then there's a force acting in this direction. Then there's a force acting in that direction. And then there's a force acting in that direction. Then you've got a force acting in this direction. Then in this direction. And then in this direction. Okay? So here's our little object. And you've got guys pushing on it. One this way. One this way. One this way, one that way, one to the left, one to the right, one up, one down, and so on, okay? So now the question is, what is the resultant? In other words, what is the one force you could apply to produce the same impact as all of these individual forces applied together? So here you can also imagine you would have 1, 2, 3, 4, 5, 6, 7, 8, right? Here you'd have 8 guys. 8 little people like this, okay? 8 little guys, each one is applying his own individual force, and what we are saying is, I want one guy to apply the resultant, meaning the equivalent force, but only one person. So let's take a look at adding these. So we are reviewing vector addition, in other words. Okay. So let's begin with this vector, then to it I will add that vector, so that one points this way. Then to it I will add that vector, which points this way. Then I will add that vector which points up. Then I will add that vector which points straight up. Then I will add that vector which points to the that way. Then I will add that vector which points to the left. And then lastly, this vector which points down to here. And take a look. What do we observe? We begin over here after we apply all of the vectors. We put them together in this little chain of vectors, right? You begin where you start, which means that the net force in this case is 0. Okay? So the net force in this case is 0. In other words, because each guy exerts a force of the same strength, but this arrow opposes this arrow, the vertical up opposes the vertical down, the one to the left opposes the one to the right, and the one this way opposes the one this way, all of the forces cancel, which is simply the same as saying, leave the object alone and apply no force to it. And the result is the same in either case. So the resultant in this case is 0. The resultant in the case of this and this is the arrow here that is double. The resultant here is also 0 because the forces cancel left and right. And the resultant for an angled one like this is this arrow given by this. Okay, and in terms of money, to make it really concrete, remember, you go to a store, you pay for an item. You can pay $5, and then you can hand over another $5 bill. But this is the same as simply handing over a $10 bill in the first place, and the result is the same. Thank you for watching.